Now, this problem right here, which I've been staring at for the past 30 minutes, is related to Schur factorization, right? And so basically, the epiphany that I had, which led me to kind of finding the solution, was that the term right here, normal, does not necessarily mean unitary, okay? They're they're not different, but we just know that all unitary matrices are normal, but not all normal matrices are unitary. And in this whole problem right here, the only unitary matrix is the matrix P. All the other matrices are normal. All right. And so first, what I want to show you guys is that a really important, basically kind of a rule is that unitary does not equal normal, right? Unitary, all the unitary matrices are a subset of all the normal matrices. And so basically, we know that a normal matrix is just the product of, let's say, a matrix A with the Hermitian transpose of itself. And we know that in a normal matrix, that product is commutative, all right? And an example of normal matrix would be a Hermitian matrix. And again, a Hermitian matrix does not equal a normal matrix. It's just a subset of all the normal matrices. Same thing with the unitary matrices. It's the same as a normal matrix, with the exception that the product results in an identity matrix. Now, now that we have looked into this, we can try finding a solution for this. Like, just try formulating a solution for this. So what I first realized was that if A is normal, then U must be diagonal, right? Because in the question, we're told that the matrix is normal, and our goal is to find that the U must be diagonal. And an important thing to note is that U is normal, right? Which is why here in the hint that they provided, they told us that the product of U with the Hermitian transpose of itself is commutative, which means that it must be normal, right? They have provided us with this information because we know that in Schur factorization of A, which is a normal matrix, the resulting matrix U is also normal. Now let me just show you why this is true. Basically, to show that if A is normal, then U must be normal, we first take the Schur factorization of A, and then we multiply both sides by A, by the Hermitian transpose of A. We can first do this. This is just one of the scenarios. I'll look into the other scenario after, but right now, if we do this, we simplify it, right? We keep simplifying it, and then we're left with the final matrix here, right? And same thing, we can do it in a different manner, in a different order, right? So if we take the Schur factorization again here, but this time, instead of multiplying the matrix on the right, we multiply the matrix on the left. And if we do that, then we get something like this after simplification, right? Now, the difference between this and this is that the matrix right here in the middle is the product right here is in different order compared to the product right here in the middle, right? And so since we know that A is normal, it contains the commutative property of A and the product of itself with the Hermitian transpose. And so this matrix right here, which relates to this, is actually equal to this matrix right here, which relates to this. And so when simplified, it just concludes that the Hermitian transpose of U and the product of itself with U is just commutative. All right, that's what we come up with. And basically, we utilize that idea to expand on this problem right here. Basically, in this problem, the sum that we're given here is crucial, right? This sum represents the values of the diagonal entries. Now, the thing about the diagonal entries is that they should be the same whether we multiply the Hermitian transpose of U first with the U, or we take the U and then multiply it by the Hermitian transpose after. The diagonal must be the same. That's because we just proved that U is normal, right? So the entries in the diagonal must be same. However, when I actually tried calculating the product of U and product of U with the Hermitian transpose of itself by taking a 3 by 3 matrix U whose entries uh, above the diagonal are arbitrary values. For example, here A, B, C, D, E, F right here. And if I take the Hermitian transpose of U here, if I take the product of it in this order, I get something like this. And if I take the product of these two in the other order, I get something like this. Now, clearly, you can see that these two are not equal. And so since they're not equal, um, they shouldn't have the same diagonal, right? However, there is one scenario in which both of these matrices are equal and therefore have the same diagonal. And this scenario is when we have B is equal to C, which is equal to E, which is equal to 0, right? All the entries above the diagonal are 0. In that case, the commutative property holds, right? And so basically, since U is normal, we only have to focus on the diagonal entries of matrix U. And if the diagonal entries are the same for both U and the if both the matrices if in different or if the product of both matrices in different orders, then U is also diagonal. And so this can be represented by this property right here, right? Note that this came from the original equation where we're just saying that if we take the if we basically take the Hermitian transpose of U and multiply with U, right? Each entry, basically taking the dot product, kind of, and that is the same thing as the diagonals in each entry of the product of matrix U with the Hermitian transpose of itself. And if these two are the same matrices, then the entries above the diagonal of the matrix U are all 0, which means that matrix U must be diagonal. So this is kind of my understanding of how this problem works, I guess, how we can approach this problem. But there's still some stuff that this proof is missing. For example, I don't know why. First, why if a matrix is normal, then we only need to focus on the diagonal entries of the matrix, right? This doesn't quite make sense to me. So yeah, if any of you guys know this, let me know down in the comments, and I can look into that. So yeah, this is just the problem I need to share with you guys.